I want to welcome everyone. Thanks so much for coming here. I see a lot of my former Fleet Numerical colleagues and my former CCL colleague Linda there. I want to welcome you to beautiful Wave Street Studios here just a stone's throw away from the beautiful Monterey Bay, very close to Cannery Row. Particularly want to thank, again, Rhett Smith, owner of Wave Street Studios, for setting this up for me, and also my friend Katie Shane for suggesting this series back some months ago. So this is lecture 2 of the 6-part series, and today we're going to be talking about climate forcing, the greenhouse effect, feedback loops, tipping points, and greenhouse gases. It's going to be pretty science heavy, so hang in there with me. And we'll jump right in talking about climate forcing and the greenhouse effect. We made references last time to the greenhouse effect. We talked about, for example, the paleoclimate and this rapid warming, this rapid post-industrial warming here. And we made reference to greenhouse effect, but we didn't really get into the science of it. And today we're going to do that. And in fact, we're going to really dig down pretty deep into the science of what drives climate change. And the framework for doing that is, in fact, the Earth's annual mean energy budget, which is depicted here. Now, what this shows is the flow of energy through the Earth system, beginning with incoming solar radiation. And this diagram basically shows how that energy flows through the system. What you need to know about this is averaged over the entire face of the Earth, averaged over day and night, averaged over all 4 seasons. And in fact, the numbers on this slide are averaged over a 6-year period from 2000 to 2005. And the numbers on here depict flux of energy in watts per square meter. And so what's a watt per square meter? Well, think about your 100-watt light bulb at home. Imagine all the heat and light coming from that projected on the ceiling on a 1 meter square. That would be 100 watts per square meter. So what you see here is we have incoming solar radiation of about 341 watts per square meter. Some of that is reflected off clouds and aerosols in the atmosphere, goes back out to space. Some is reflected from the surface, goes back out to space. Some is absorbed at the surface. Some is absorbed directly by the atmosphere. This is called the sensible heat flux. That's heat that you can sense. It's like, for example, you put your hand over a hot asphalt road in the summertime. You can feel the heat rising. Kind of spirals here. Everyone's seen, hawks, for example, circling on thermals. That's what's going on here. That's a sensible heat flux that transfers heat from the surface of the Earth into the atmosphere. This is called the latent heat flux or the evaporative heat flux. When you come out of a swimming pool and the wind hits you, you cool down, and that's because the water on your skin is evaporating. That carries heat away. And that's what's happening here. As water evaporates from the land and from the ocean, it cools, it exerts a cooling effect. And then finally on the right here, we have the flow of infrared radiation or long-wave radiation. And the Earth is radiating this long-wave radiation. Some of it is absorbed in clouds. Some of it is then emitted from the top of clouds. Some goes directly out into space. Some is emitted by the atmosphere. And a large amount of it is trapped by greenhouse gases, such that about 80% of the long-wave radiation or infrared radiation leaving the Earth actually comes back down because the effect of these greenhouse gases. So this is the Earth's energy budget. Now, you may have a couple questions. And the first question you may have is, what about other sources of heat? For example, what about heat from the Earth's interior? Well, it turns out it's negligibly small. In fact, the heat from the Earth's interior is about 13 times smaller than the current rate of heating of the Earth. What about waste heat from factories and buildings, transportation, et cetera? It's about 40 times smaller than current rate of heating. What about frictional heating from tidal circulation? The tides are running around there. There's tidal friction. What about that heating? Well, it's about 170 times smaller than the current rate of heating of the Earth. Everything you can think of as a potential other sources of heat are really, really small compared to the current rate of heating of the Earth. And as a result, we can neglect them. They're negligibly small. That being the case, if you think about it, here you've got the Earth hanging out in space here. With the internal sources of heat being negligibly small, what really counts is the radiation balance, the heat energy coming in minus the heat energy going back out. And you can schematically depict it like this. The long arrows here represent this energy coming from the sun, not drawn to scale, of course. And the small yellow arrows here represent solar energy that's reflected from the Earth back out to space, mainly from clouds, but also particularly from snow and ice-covered areas. Well, the long arrows here, this energy coming from the sun, is in fact exactly this number right here. So this equates to that. And the reflected solar radiation going back out to space, which of course happens only on the daytime side of the Earth, not on the nighttime side of the Earth, is in fact this number right here. And then finally, we have these red arrows here, which depict the outgoing long wave or infrared radiation, which is happening all the time, all the way around the Earth. Now, imagine this red circle here being the top of the atmosphere, not drawn to scale. And imagine totaling these fluxes of energy around that top of the atmosphere sphere around the Earth. That has a particular name, and that name is called the Earth's Energy Imbalance, or EEI. And in fact, for the 6-year period depicted here, it's just the sum of these numbers. It's basically the energy in minus the energy out. And so if you add these numbers up here, you come out with 0.9 watts per square meter. And in the particularly important point here is that that is in fact exactly how much the Earth is warming. This EEI parameter, Earth's energy imbalance, which is essentially the sum of these three numbers at the top of the atmosphere, equates to how much heat the Earth is absorbing and warming with. And we can measure this. We can actually measure the radiation balance at the top of the atmosphere from satellites. Beginning in the 80s, a series of satellites were launched called Earth Radiation Budget Experiment, and there's a follow-on experiment called CERES, Clouds Earth Radiant Energy System Experiment. And those satellites can actually measure these components very accurately. And at the same time, recognizing that about 95% of the heat of the Earth that the Earth is absorbing, in fact, is going into the ocean, we can measure the change in heat content in the ocean, particularly from drifting buoys that are actually profiling up and down in the upper 2,000 meters. It's called the Argo float system. So, and in fact, there's a little bit of calibration involved in marrying up this satellite data with the in situ data here. But when you do that, you find that the two numbers track along perfectly well. That in fact, this EEI parameter, the radiation imbalance at the top of the atmosphere, tracks along perfectly with the rate at which the Earth is taking up heat. So this is an extremely important parameter, EEI. Really, this imbalance up here at the top of the atmosphere drives climate change. So the Earth's energy imbalance, and thus the climate system, is externally forced by four factors. When I say externally forced, I'm talking about forcing that is external to the climate system. And these four factors are the sun. The sun can cause the Earth to warm. The sun radiance fluctuates over time. There's the 11-year sunspot cycle. But there's also longer trends in total solar irradiance. That's the heat coming from the sun. And that will certainly affect the climate. Second thing are aerosols in the atmosphere, mainly ash from volcanic eruptions and air pollution, and that tends to reflect solar radiation back out and cool the Earth. The third factor is changes in surface albedo due to land use. So for example, when we humans practice deforestation and turn forests into cropland or cropland into grasslands or even grasslands into deserts, that changes the reflectivity or the albedo of the Earth, and that can either exert a warming or a cooling effect. And then finally, there is the absorption of the outgoing radiation by greenhouse gases in the atmosphere. These are the four external forcing factors that affect, in fact, control EEI and thus drive climate change. So the question then is, what is causing the global warming and climate change we see that we've been concerned with over the last 100 years or so? Well, it's not the sun. And that's proven by a wealth of data. We've been measuring sunspots, which are highly correlated with the output of the sun, since 1600. We've been measuring solar output from space, from satellites, since the 1980s, as I mentioned. And there's many other ways of looking at this. The fact of the matter is the sun can affect the climate. It played a role in the medieval warm period, which was from 1900 to 1200 AD. It played a role in the Little Ice Age, which was from 1500 to 1700 AD. And in fact, in the first part of the 20th century, about 20% of the global warming observed was caused by the sun's radiance increasing. But it peaked out around in the 1960s and has been pretty level or even slightly declining since then. So it's not the sun. The sun is not producing the global warming we are concerned with. Well, it's not aerosols. They produce cooling. Aerosols, they reflect the solar radiation away. They produce cooling. There was the period of time from the beginning of World War II to about the early 70s where there was actually cooling going on, and that's because there was so much air pollution being put into the atmosphere globally because of World War II production, the post-industrial boom, until laws were passed to bring that air pollution down. That was masking the effect of global warming, these aerosols in the atmosphere. Now, there is one exception to this, and that is soot, also known as black carbon. And soot in the atmosphere, the black carbon, can produce a warming effect, but it's very small and very localized. On balance, aerosols produce net cooling, so it's not aerosols. Well, what about land surface change? Well, it's pretty small. And generally speaking, when we tear down forest or we do the kinds of changes that are typically done by humans with regard to a land surface, that tends to produce a slight cooling effect, not a warming effect. So what's causing the global warming? Well, in fact, it is indeed the buildup of greenhouse gases in the atmosphere caused by human activities. So here are these greenhouse gases, and I've put them in the order of how much infrared radiation they are trapping, how much global warming they're causing. Top of the list is water vapor, then carbon dioxide, CO2, methane, the fluorinated gases, or F gases. These are gases that contain the atom fluorine in the molecule. They're typically used in refrigeration. And finally, nitrous oxide. Note that I've colored water vapor differently, and that's because water vapor is a special case here. Water vapor in the atmosphere, which of course we perceive has humidity, absorbs more infrared radiation than CO2, more infrared radiation than any of the other greenhouse gases. And indeed, it's a major reason why we're not in a permanent ice age. If you took the greenhouse gas property of water vapor away suddenly, the Earth would cool, and in fact, we'd be trapped in a permanent ice age. So water vapor helps maintain the Earth's temperature and amplifies the rate of global warming through the water vapor feedback loop, which we're going to talk about in some detail in a minute. However, water vapor does not drive global warming because it is in balance with the natural hydrologic cycle, and this is a depiction of the natural hydrologic cycle here. Water vapor is in balance with the natural hydrologic cycle for two reasons. First, humans are not intervening in this cycle in a significant way. We aren't putting huge amounts of water vapor into the atmosphere the way we're doing it with the other greenhouse gases. But also, the time scale for the atmosphere to adjust to imbalances in water vapor is very short. If we did put a huge amount of water vapor in the atmosphere, well, it would rain out and snow out in about 10 days. That's sort of the lifetime of water vapor in the atmosphere. Greenhouse gases, on the other hand, for example, CO2, time frame for that CO2 to stay in the atmosphere is 100 years or more. So water vapor is an important greenhouse gas, and it does participate in global warming through the water vapor feedback loop, but it does not drive global warming. What indeed drives global warming are these greenhouse gases here. That's carbon dioxide, methane, the fluorinated gases, and nitrous oxide. Now, in addition to that greenhouse effect, the Earth is also affected by feedback loops. Feedback loops which can either amplify global warming or attenuate, for a positive feedback loop, or attenuate global warming if it's a negative feedback loop. Now, here's an important point. Climate feedback loops do not drive global warming. Rather, they amplify warming in the case of a positive feedback loop or attenuate warming in the case of a negative feedback loop. They require a positive value of EEI, this radiation imbalance here to drive the global warming. And generally speaking, when you have a positive value of EEI, that's triggering some event A here, which then causes an increase in B, which causes an increase in C, which then feeds back and amplifies A. And so you end up going around this loop here, and it amplifies the warming. So there are a number of positive feedback loops or effects out there that are affecting climate, affecting global warming. But there are two that are particularly important, and the most important one is, in fact, the water vapor feedback loop. And it works like this. Because when you have increasing global temperatures because of this imbalance in the radiation at the top of the atmosphere, this produces increasing evaporation of water from the oceans and the land. The oceans are warming, and we saw that in lecture 1. We looked at some of the animations there. As this evaporation is increasing, that produces increasing water vapor in the atmosphere. And of course, as the atmosphere is warming, it can hold more water vapor. So the water vapor in the atmosphere is slowly increasing as a result of this feedback loop. But when you put more water vapor in the atmosphere, that traps more heat. And that produces additional warming, which produces additional evaporation, which puts additional water vapor in the atmosphere, which then produces additional warming. So it's a positive feedback loop, and it's been significant. We're about almost a third or so, a third to a half of the warming we've experienced over the last 120 years has been a result of the water vapor feedback loop amplifying the warming that's caused by the greenhouse effect. The second one that's particularly important is the snow-ice feedback effect. And you can kind of see it here. Ice and snow, particularly sea ice, is very bright, has a very high albedo, and reflects the sun rays away. But when that ice melts, it leaves behind a dark ocean. The ocean is very dark, and that increases the amount of solar radiation absorbed. So you're increasing the global temperatures, that's decreasing the snow and ice. That's then increasing the amount of sunlight absorbed by land and sea. You can kind of get that sense right here, which further increases the global temperatures. And you go around this feedback loop, and it amplifies the warming. And it's an important feedback loop. Now, I've mentioned the word albedo here. Let's take a little bit closer look at that. Albedo is the measure of the diffuse reflection of solar radiation out to the solar radiation and measure on a scale from 0 to 1. So a value of 0 would be absorbing all of the solar radiation. A value of 1 would be reflecting it all away. The Earth's albedo ranges from about 0.08 to 0.85. Here's a picture made from satellite data, which actually shows an instantaneous picture of the albedo on 5 March 2011. And you can see these areas of very dark ocean here, absorbing a lot of solar radiation. They have a low albedo. This white band here is called the ITCZ, the Intertropical Convergence Zone, very cloudy region. The clouds are reflecting the sun away. Notice a lot of reflection from the Greenland ice sheet here, for example, areas where there's snow on the ground, lots of reflection. So here's how albedo varies. Snow has a very high albedo. Water has a very low albedo. Ice is kind of in the middle here. And so this is kind of different ways that the albedo changes as a function of different land types. Now, there are other positive feedback loops out there. For example, there's CO2 feedback, forest feedback. Forest feedback is, we're having a drought, trees are dying. When those trees die, eventually they're going to rot, and that carbon that was stored in the trees goes into the atmosphere. That triggers more warming, which triggers more severe drought in dry areas, which then causes more trees to dry. Perhaps we have a forest fire, and the burning of the trees puts more CO2 into the atmosphere. Lake feedback. Lakes are a source of methane, and as the climate is warming, lakes at higher and higher latitudes are emitting more and more methane. Here's one I dreamed up. It's called the air conditioner feedback. You've heard it. You're going to hear it here first. I made it up. And it works like this. As the planet gets warmer, people tend to buy more air conditioners, particularly in developing countries, particularly in Asia. And what does that do? Well, it puts more of a load on the electrical system, so more fossil fuels are typically burned to provide the electricity to power those air conditioners. That makes the Earth want to warm more. Oh, by the way, lots of times those air conditioners are discarded, and the fluorinated gases in them, the coolants, find their way into the atmosphere, and that accelerates the warming even more. People want to buy more air conditioners. So that kind of thing can happen. So I know what you're thinking here. Well, I'll come back to that. But I want to now talk about tipping points. You've probably heard the term tipping point. A tipping point is the global warming threshold that, if crossed, would trigger a strong positive feedback loop that was not previously active, or at least not significant. And this feedback loop would then abruptly accelerate the rate of warming, producing an inflection point that steepens the long-term upward trend of global warming as a function of time. So crossing tipping points might result in what appears to be runaway climate change on timescales of a few centuries. Notice I've qualified this by saying timescales of a few centuries, because I want to tell you right now, there's pretty much nothing we humans can do to the Earth that the Earth can't recover from, no matter what we do. And that includes nuclear holocaust tomorrow. There's nothing we can do the Earth can't recover from. The problem is it could take tens of millions to hundreds of millions of years to recover, and that's not going to do us humans much good. So, as I often say, the Earth is going to be just fine no matter what we do. It's we humans that are going to suffer. Now, there are two tipping points that are most concerning, and the first is called permafrost feedback. It turns out there's a huge amount of carbon stored in permafrost in Siberia, in Canada, even in Alaska. Where did that carbon come from? Well, in lecture 1, we talked about periods of hothouse Earth, where the Earth was so warm, all the ice had melted. There were rainforests extending up to the Arctic Circle. There were dinosaurs living, in high latitudes. There were crocodile-like creatures in the Arctic. Eventually, all that flora and fauna died out, and it was trapped in and preserved in permafrost. Permafrost is pretty much, the best way to think of it is like frozen mud, essentially. And as the planet is warming, the permafrost is starting to thaw, and that produces two problems. One is lots of infrastructure, in Canada and Alaska, Siberia, is suffering because as the permafrost thaws, what was previously solid ground to build your house or your road or your bridge on suddenly starts to cave in, and there's a lot of issues on melting, thawing permafrost affecting infrastructure. But the other big problem is when the permafrost thaws out, microbes that have essentially been in suspended animation since the ancient times, they wake up and they start to feed on the carbon material that's there in the permafrost. Second largest carbon store in the world in the permafrost, larger than all the forests in the world, second only to the deep ocean. Now, when those microbes begin to feed on those ancient flora and fauna, in the presence of oxygen, they produce CO2, which is bad enough. That CO2 finds its way to the atmosphere, and that becomes another major source of CO2. But if it's deeper down, in an oxygen poor environment, or even an anoxic environment, when those microbes feed on that material, it produces methane, which is even worse. Methane, as we're going to talk about in a minute, is much more powerful greenhouse gas than CO2. Eventually, it's going to find its way into the atmosphere. And here's an example of that. There's lots of videos like this out on YouTube where people will go up there and take an ice axe and puncture the permafrost, and there'll be outgassing of something, and you hold a flame to it and it explodes into flame. It's methane. There's a lot of it coming out there. So the concern is, will we hit a tipping point where so much of the methane and CO2 in the permafrost is released that it just accelerates the warming? That certainly could happen. The question is, when would that happen? How much warming does it take for that to happen? I don't think anyone really has a good handle on that. I've only heard one estimate of that, and that one estimate was 5 degrees C above pre-industrial. I don't think we're going to get there. I think we're going to hold warming to significantly less than that. But nevertheless, this is something to be concerned about. The second possible tipping point, which I think is of concern, is a cloud feedback effect. Clouds are complicated. with regard to the climate problem, because high clouds exert, like cirrus clouds, we see in the wintertime, high clouds exert a warming effect. Low clouds exert a cooling effect. For example, the marine stratus that's so common here in Monterey, they exert a cooling effect because they reflect all the solar radiation, from the top. The problem is, as the models are showing that as the Earth warms, that tends to produce a thinning of the low clouds, a thinning of the marine stratus. And this is just a computer depiction of that. Here's kind of where we are right now, 400 parts per million concentration of CO2. But if we were to go to 1,600 parts per million, that's a factor of 4 up. That might be where we'd be, the latter part of this century if we didn't constrain emissions. That warming would produce significant thinning of the marine stratus, and that would result in a very strong positive feedback effect and a very strong warming effect. Some of the models that are being used now in the latest rounds of modeling, which by the way we'll be talking about next week in next lecture, they're showing this effect, and so that is of concern, that it's a potential tipping point that could come into play there. So I know what you're thinking. I can see the look on your faces here. You're saying, particularly Chuck here. You're saying, hey, look, this system must be incredibly unstable. If there's all these positive feedback effects here, it's like taking an ice pick and trying to bounce on its end here. You just can't do it. It starts to tip over and there's a positive feedback and it's just going to go. So the climate must be incredibly unstable because of these positive feedback effects. Well, it isn't. It's actually pretty stable. And that's because there's a very powerful negative feedback at work. And that's called the long wave radiative feedback. And it's based on a famous equation from physics. This is the only equation I'm going to be showing you today, so don't get mad at me. It's called the Stefan Boltzmann Law. And it says that the radiation from an object is proportional to the 4th power of its absolute temperature in degrees Kelvin. Now, the Kelvin or absolute temperature scale is just like the centigrade scale, except that the 0 point is at absolute 0, which is minus 273 degrees centigrade. So if you put that, if you recognize that the average temperature of the Earth is about 15 degrees centigrade right now. So if you put those numbers in there and realize how much it's increased because of the fact that we've warmed about 1.1 degrees centigrade, you find that the outgoing long-wave radiation here is increased by about 1.7%, and that's actually pretty large. And that's basically tried to cool the Earth. So because this is a negative feedback effect, when the Earth tries to warm up, this feedback effect here tries to cool the Earth back down. And because it depends on the 4th power of the temperature, small changes will produce a pretty large, small changes in temperature will produce a large change in outgoing surface radiation. So as the Earth tries to warm, this tries to cool it back down. If the Earth was trying to cool, this would try to warm it back up. So thank goodness for this negative feedback effect. If we didn't have this negative feedback effect, first of all, the system would be extremely unstable, but also we would have warmed now by probably somewhere in the range of about 4 to 5 degrees centigrade above pre-industrial, even now. And that's kind of the worst case scenario, business as usual scenario where we would be at the end of this century. Well, without the effect of this negative feedback here, we'd be there right now, which would be really bad. So it turns out this system is actually pretty stable. And for example, if all 4 of the external forcing factors we learned about, the solar radiation, the aerosols, greenhouse gases, land use, were suddenly to remain constant in time. So we had a magic wand here. We waved that magic wand, and all these external forcing factors remain constant in time. What would happen? Well, the Earth would continue to warm, but at a slowing rate. And after a couple of decades and probably a few tenths of a degree warming, it would stabilize. And it would stabilize because this radiation balance at the top of the atmosphere, the EEI we talked about earlier, would come down to 0. So fortunately, because of that negative feedback effect, that long-wave radiative feedback effect, the Earth is actually pretty stable. The problem has been we humans are continually increasing the amount of greenhouse gases in the atmosphere. And as a result, we are continually nudging the system out of balance, continually nudging the system towards more warming. and basically nudging the radiation balance here at the top of the atmosphere towards more imbalance, which is causing more heat to be absorbed in the Earth. So let's talk about these greenhouse gases. Here's a depiction of the approximate contribution of the long-lived greenhouse gases to the current rate of global warming, stressing the word approximate here. So you can see it's carbon dioxide, methane, also known as natural gas, the fluorinated gases, and nitrous oxide. What you see here is that CO2 is in fact the dominant driver of global warming. That's why we talk about CO2 most of the time. CO2 is driving more global warming than all of the other greenhouse gases combined. Now this is a snapshot in time. There's another way of looking at this, and that is the idea of global warming potential. The global warming potential of a gas refers to the total contribution to global warming over a specified period of time, resulting from the emission of 1 ton of the gas relative to 1 ton of the reference gas, which is CO2. CO2 is assigned a value of 1. Global warming potential takes into account both the greenhouse potency of the gas and its nominal lifetime in the atmosphere, but not how much is currently in the atmosphere. And typically, we talk most of the time about GWP 100, which is global warming potential over 100 years. But sometimes people talk about GWP sub 1,000, global warming potential over 1,000 years. If you just see the term global warming potential or GWP, then pretty much by default they're talking about global warming potential over 100 years. So what we see here is that carbon dioxide has a GWP of 1. Methane has a value of 28. So what does that mean? It means you put 1 ton of methane into the atmosphere, it's equivalent to putting 28 tons of CO2 into the atmosphere. Nitrous oxide, 265. Put 1 ton of nitrous oxide in the atmosphere, it's like 265 tons of carbon dioxide. Look at these fluorinated gases. Huge, huge global warming potential. So just quickly, I want to talk a little bit about lifetime of these gases in the atmosphere, particularly CO2. We talk about, often you'll hear people say lifetime of CO2 in the atmosphere is 100 years. That's kind of the nominal lifetime of the gas. But the way it works is if you put a large pulse of CO2 into the atmosphere and then look how it varies as a percentage of time, it actually starts decreasing pretty rapidly for the very beginning here. But that decrease falls off over time, such that after about 100 years, you still have about 30% remaining. And that's kind of the standard for nominal lifetime. But in fact, if you go out 1,000 years, you still have about 15% remaining. So, when you're driving your car, you're putting CO2 in the atmosphere through the tailpipe. Most of it is gone in 100 years, but some of it is still going to be out there even 1,000 years from now. Now, the F gases, the fluorinated gases, are particularly scary. They're actually not producing a whole lot of warming now. They're pretty low on the list. But they're particularly scary because their global warming potential is so large. Somewhere in the range of 1,300 to 23,500. So let's talk about these F gases. They are a family of man-made gases used in a range of industrial applications. Because they do not damage the ozone layer significantly, they are often used as substitutes for ozone-depleting substances, for example, chlorofluorocarbons or CFCs. However, these F gases are powerful greenhouse gases with huge global warming potential. They fall mainly into 3 groups. Hydrofluorocarbons, HCFCs or HFCs, which are used as coolant in air conditioners, refrigerators, and freezers. And that's a real concern, because if people take refrigerators and they just throw them on the landfill when they're broken down, eventually those gases are going to get into the atmosphere, guaranteed. What really needs to be done is those devices need to have that gas extracted, recycled, or neutralized, and there's expense associated with that, so there's a temptation for these refrigerators to be just discarded, and that's a big problem. Second class are perfluorocarbons, PFCs, also known as fluorocarbons or FCs. These are used in manufacture of semiconductors and in certain medical procedures. Really important that they don't leak into the atmosphere. And finally, there is sulfur hexafluoride, Sf6, which is used as a gaseous insulator in medium to high voltage devices such as transformers, circuit breakers, and switches. Sf6 is the most potent greenhouse gas known to mankind. It's unbelievable. 23,500 global warming potential. It's used in devices that switches and circuit breakers and so forth. The problem is as we go to more clean energy with, for example, solar arrays and wind turbines and so forth, more of a distributed system, there's more of a tendency to need to use these kinds of gases because they're used in the devices that hook everything together. So why don't we just use some other type of gas? Why don't we just use an alternate? Well, are there alternatives? Yes, there are. There are other gases that can be used rather than SF6 for these applications. The problem is they're more expensive and they're less effective. So basically what you're doing, you're asking the electrical industry to spend more money to produce devices that are more likely going to cause an electrical fire. A little bit of a hard sell, but it is going on, and I've heard that PG&E has made some commitments about keeping SF6 usage down, and that really needs to be pushed hard because SF6 is by far the most potent and longest lived greenhouse gas known to man. Once it gets into the atmosphere, it's going to be there for tens of thousands of years. So the bottom line here is good stewardship of equipment and materials containing the fluorinated gases, especially proper maintenance and disposal, is essential to combat global warming. Now there's another term here you'll come across, and I just want to hit it real fast. It's CO2 equivalent, usually written CO2e like this. And it gives the number of tons of CO2 emissions required to equal the specified emission of another greenhouse gas in terms of its global warming potential over 100 years. And it's real simple to calculate. You simply take the global warming potential number for a particular gas and multiply it times that emissions flow. So for example, if you have some operation here, a farm, say it's emitting 1 million tons of methane per year, that's the equivalent of emitting 28 million tons of CO2 per year in terms of its impact over warming for 100 years. Simply multiplying the amount of emission times the global warming potential number. So from here on, I'm going to focus mainly on CO2, since CO2 is the dominant greenhouse gas in terms of how much warming is going on currently. And what you see here is a depiction of CO2 in the atmosphere, concentration in parts per million from 1700 to 2019. In the pre-industrial era, right about here, CO2 concentration was very stable at about 280 parts per million. Then beginning right around 1900, as the Industrial Revolution started to crank up in a big way, we started burning lots of coal, CO2 started increasing rapidly, and particularly after World War II, it started increasing very rapidly, such that we're now running well above 400. I think we're around 419 or something like that right now. The total mass of CO2 in the atmosphere is also of interest. From 1850 to 2019, the total amount of CO2 emitted by human activities amounted to about 2.4 trillion tons, not billion, 2.4 trillion tons of CO2, and about 0.9 trillion tons, almost a full trillion tons, is still there. The current rate of CO2 emission into the atmosphere as a result of human activities is about 40 billion tons per year. Now you may hear a number 51 billion tons. That's the total greenhouse gas emissions, including the methane and nitrous oxide and so forth, cast in the form of CO2 equivalent. You add those 11 billion CO2 equivalent tons, you come up with about 51 billion tons of total greenhouse gases going to the atmosphere. But in terms of CO2 itself, it's about 40 billion tons per year. You may hear the term Keeling curve. That refers to this part of the curve right here, which was a result of very detailed measurements by a gentleman by the name of Charles Keeling, an oceanographer from Scripps Institution of Oceanography. He was the first to identify the fact that there is an annual cycle in CO2. It peaks in the spring, is minimum in the fall, northern hemisphere spring and fall, and that has to do with the annual cycle of vegetation going on. So where's all that CO2 coming from? Well, in terms of annual emissions, China's number one. There's no doubt about that. China's number one, sticks out like a sore thumb. About a factor of 2 greater than the second place country, which is indeed the United States. Then it's India, Russia, Japan, and it goes on down from there. So before you get too mad at China, ask yourself this question: why wouldn't China be the world's largest emitter? They are the world's most populous country. So another way of looking at it is per capita emissions. Per capita emissions, you simply take the total emissions of a country, divide by the number of people in the country, and that's how much emissions there are per capita. Well, there's a lot of people in China. So when you do that, China falls way down the list and becomes pretty characteristic of a European country. And guess who's number one? The United States. The United States, Australia, and Canada really stick out like sore thumbs here. What's the commonality there? A lot of people have asked that. I think it has to do with the fact that US, Australia, and Canada, we have high standards of living, but also low population density, large areas of open space. And I think that probably has something to do with it. But our per capita emissions are quite high, close to 17 tons per year per American. There's a third way of looking at it, and that is the cumulative CO2 emissions over this period of time from 1750 to 2018. And guess what? US is again number one, and by a pretty wide margin, followed by China, former Soviet Union, and then pretty much the European countries. So US is number one in 2 of those 3 categories and number 2 in the other category. So clearly the US has a role to play here. The US needs to lead on this issue. The US needs to set the example for the rest of the world, be active in trying to achieve the goals of the Paris Climate Accord. It's very unfortunate we pulled out of the Paris Accord a few years ago. It's really good we're back into it now. So clearly the US has a role to play. So where are the emissions in the US coming from? Well, first of all, about 81% of our emissions are in fact carbon dioxide. Then it's methane, nitrous oxide, and the fluorinated gases. Fortunately, the fluorinated gases are low here. We need to keep them low. And these are all cast in the form of CO2 equivalent, which we learned about. Well, the vast majority of CO2 emissions in the US are coming from these 3 sectors. That's transportation, electricity generation, electrification of the power grid essentially, and industry, primarily cement and steel production, which produce a lot of CO2. This picture is not all that representative of the rest of the world. The rest of the world, transportation is down pretty low, down around about 12%. The rest of the world, agriculture is higher. But we have a lot of cars, we drive a lot, and we have wide open spaces, a lot of transportation occurring over long distances. So transportation is in fact our number one source of CO2. And by the way, this is the kind of thing we're going to be talking about in more detail in lectures 4 and 5. We're going to be talking about the technologies that are available to mitigate these kinds of emissions. So where does all that CO2 we're emitting go? Well, this is a depiction of the fast carbon cycle. We learned about the geological carbon cycle in the last lecture, which had a time scale of 100 million years. This is a much faster carbon cycle. That's why I call it the fast carbon cycle. And it kind of works like this. First of all, all the numbers here are millions of tons of carbon, not CO2. The gold numbers reflect the natural flow of carbon in the absence of human emissions of CO2, and the red numbers show the fate of carbon from human emissions of CO2. So you can see here, humans are emitting about 9 billion tons per year of carbon, which equates to about 40 billion tons of carbon dioxide. About 3 billion tons of that is taken up by photosynthesis and, in fact, sequestered in soil carbon through the root systems of plants and trees, and that's really good. That's what we really want to see have happen. About 2 billion tons is absorbed in the ocean. And that's good that it's not going to the atmosphere, but it's not so good because it's having an impact on the ocean. It's causing the ocean to become, to trend towards the acidic side. That's called ocean acidification. And we talked about that briefly last week. that puts a real stress on marine calcifers, so that's a big problem. And then finally, the remaining amount, which is about 4 billion tons, is going into the atmosphere and staying in the atmosphere. It's increasing the amount of CO2 in the atmosphere, and that's really bad. That's indeed what is driving, to a great extent, the global warming and climate change we are experiencing. So in terms of round numbers that are easy to remember, about 35% of our carbon emissions are being taken up by the land. That's really good. That's what we want. We want to enhance that. About 20% is taken up by the ocean. Not so good. And finally, about 45% accumulates in the atmosphere, and that's really bad. That's what, in fact, is causing the global warming we are concerned with. So I want to make a few closing comments here now. There's an overwhelming international scientific consensus on the following 3 points. Point 1, over the past 120 years, the Earth has been warming and the climate has been changing at alarming rates. Point 2, global warming and the resulting global climate change over the past 120 years have been driven almost exclusively by the Earth's greenhouse effect and the accumulation of greenhouse gases in the atmosphere caused by human activities. And finally, point 3, without dramatic reduction in the emission of greenhouse gases into the atmosphere, the Earth will continue to warm and the climate will continue to change to the detriment of humankind. Stated succinctly, it's happening, humans are causing it, and it's not a good thing. Now, overwhelming international scientific consensus. There isn't a legitimate science organization in the world would disagree with those 3 points I just read out. And in fact, this is a partial list of leading science organizations all around the world that have made formal declarations confirming human-induced global warming, including the most prestigious science organizations in the US, the US National Academy of Sciences, the US National Research Council, American Association for the Advancement of Science. All of the societies that are involved with the atmosphere and the ocean, such as the American Meteorological Society and the American Geophysical Union, all confirming human-induced global warming. So I want to sort of end with showing you something which kind of sets the stage for next week's lecture. We're going to be talking a lot about climate models, climate modeling, ensemble modeling, that sort of thing next week. And this is kind of a taste of that. And this gives us a sense how we're able to so confidently know that humans, in fact, are causing global warming and climate change. So what we're looking at here, there are three lines, a black one, a brown one, and a green one. So think about that. From 1850 to 2020, the black line is the observed temperature above the pre-industrial level. So we looked at this a little bit last week, and we saw that beginning in about the 1970s, there was this rapid warming here. We saw the up and down zigs and zags, and we talked about that last week as being a result of climate variability as opposed to climate change. So that's the black line. The brown line here is a result from models plural. It's a result of averaging the runs of a large number of climate models over this period of time. This is called hindcasting. The way that works is you start the models back here, and then you used the observed forcing. And we talked about this 4 forcing parameters, how the sun is changing, how the greenhouse gases are changing, how the aerosols in the atmosphere are changing, how the surface land use is changing. You use that those 4 observed forcing parameters all over for this period from 1850 all the way up to 2020. And you run these large numbers of models. In fact, in this case, it's about 50 or so models. And then you take the average of that. It's called the ensemble average or ensemble mean. We're going to talk a lot about that next week. And what you get from that is this brown curve. And you can see that it shows quite accurately, the ensemble mean, this average here, over a period of 170 years or so, it is very accurate in predicting where the Earth's temperature ends up. Now, the green curve is the same thing, same models, same process, except the greenhouse gas input is withheld. Same forcing for the sun, same forcing for aerosols in the atmosphere, same forcing for land use, but we hold the greenhouse gases constant. We pretend that we're not putting greenhouse gases into the atmosphere. And what you see here is that For the first part of the record, there isn't that much difference. And you can kind of see, it's kind of warming here, and you can kind of see the brown line is a little bit closer there, but they're pretty close together. However, beginning right about here, in the late 1990s, suddenly the Earth really started, well, I guess in the 70s actually, the Earth starts to warm very rapidly. The models that include the greenhouse gases capture that very accurately, but the models that don't just basically don't show it. Now, the other thing on here, there is this envelope of light brown here, and there's envelope of green here. That shows the range of the model predictions. So there are some models that at any point in time are showing warming way up here. There are some models that are showing warming way down there. And the brown curve here is the average of that. But the envelope here, if you can think of this as sort of being the envelope, that shows the range of the model predictions. And the same thing for here. This shows the range of model predictions when we run the models without including the changes in the greenhouse gases. So you can kind of think, I'm going to introduce a little bit of a wonky term here, and that's a little bit, geeky kind of term, signal to noise ratio. You can kind of think of the difference between the model runs that don't change the greenhouse gases and the model runs that do change the greenhouse gases as the signal. That's kind of the signal of human-induced climate change. And you can kind of consider this envelope of uncertainty here as being the noise. Well, back in this time frame, the signal, you couldn't really separate the signal from the noise. But beginning, here, I guess probably about the late 90s, suddenly the signal separated pretty clearly from the noise. The signal-to-noise ratio became, greater than 1. And it became quite clear, these areas of uncertainty don't overlap. And so it becomes pretty clear, very clear indeed, that it is in fact these greenhouse gases that are causing this warming. So that's one way of looking at it. And there's actually an even more quantitative way of looking at it. And I'm particularly going to talk about these two gentlemen right here. This is Professor Suki Manabe, senior scientist at Princeton University. He pioneered the use of computer models to predict the fingerprint of anthropogenic or human-caused global warming in patterns of long-term atmospheric temperature change. And we saw a little bit of that last week. Remember, we saw that the global warming is happening most strongly at the surface, and it falls off with altitude as we go up in the atmosphere. It actually becomes cooling as we go into the stratosphere. We also saw that warming is amplified as we go towards the North Pole. It doesn't happen in the southern hemisphere. We saw that warming was stronger over the land than over the sea. So Manabe started with very simple models and then progressed to more sophisticated couple models to sort of show the fingerprint of anthropogenic or human-caused global warming in what you would in these model predictions. In '79, this gentleman here, Professor Klaus Hasselmann, founding director of the Max Planck Institute for Meteorology in Germany, developed a rigorous statistical technique for detecting these fingerprints from atmospheric temperature measurements provided by satellites. And the work of these two guys led to many, many studies by a number of researchers over subsequent years, that confirmed anthropogenic global warming with increasing confidence as the Earth continued to warm, as that signal we looked at before became larger, and also as the satellite data record grew longer. And in fact, by 2016, the Earth had warmed sufficiently, and enough satellite data had been accumulated and analyzed to achieve the statistical 5 sigma level of certainty that humans are indeed causing global warming. Now, 5 sigma is the statistical gold standard for validating a scientific claim. It implies a 99.9999% confidence in the claim, or only a 1 in a million chance that the claim is wrong. It's the same standard applied by particle physicists to identify the existence of new particles, such as the Higgs boson, for example. So, footnote, Manabe and Hasselmann were awarded a share of the 2021 Nobel Prize in Physics for their research on global warming and climate change. So I want to end with a word to those climate change deniers who are undoubtedly going to eventually find this video on the internet. And what I say to you is, if you have the data, if you have the insight, if you have the knowledge to overturn this international scientific consensus at the 1,000,000 to 1 level of certainty, do it. Publish your work in the peer-reviewed literature. There's a Nobel Prize out there waiting for you. It's waiting for you to be claimed. It's waiting for you. Not to mention fame and fortune. So have at it. Have at it. Okay, that's it. Thanks so much, and I appreciate everyone for coming. Thanks a lot. So I want to open it up now for questions and discussion. Yes, yes, sir.
So I work in horticulture, and so landscape horticulture has a horrible environmental impact, and I would say, I guess, part of a movement to improve that. And there are some principles that have been put out there to help do that. All across the board, reducing truck trips, reducing the amount of water that plants use, reducing the amount of fertilizer, the whole thing. Moving pretty soon to electric rechargeable landscape equipment, gardening equipment. And there's one where some people believe that we can sequester a significant amount of carbon in the soil by changing our practices, by feeding the soil with organic matter, for example. I hope it's true, but can you give me a sense of that potential, particularly in gardening as opposed to agriculture, or maybe with agriculture as well?
Yeah.
There's the big claims for that, and I'm worried that some people are relying on it as kind of like the silver bullet to solve the whole problem. Keep emitting. They don't say that, but I mean, if there's this idea we can sequester carbon, we can somehow get it out of the atmosphere, we don't have to change the rest of our economy. Right now.
Well, first of all, there's no silver bullet out there. There's a whole bunch of things we need to do, and what you mentioned is one of them. And in fact, I'm going to be talking about that either in lecture 4 or lecture 5. There's a whole discipline called regenerative agriculture, and the idea there is you want to minimize the soil disturbance. You want to minimize the use of fertilizers. You want to use cover crops. You want to do enhanced crop rotation. There's lots of things that can be done to increase the sequestration of carbon in the soil. That's an important part of the solution. But that's only one of many, many solutions that needed to be pursued. And we're going to talk about it, 80 or so of the solutions in lectures 4 and 5. But agriculture is an important part of it. Agriculture accounts for about 25% of global emissions. A big part, about half of that, is actually cattle production. So yeah, absolutely, there are some things that can be done there, and we're going to talk about that later on. Yes, Chuck.
So, I'll get it closer here. Yeah, Mike, you were talking about the tipping points.
Yes.
Right, and it's really scary stuff, of course, to talk about these events that could really accelerate things. There's a couple that I've heard about anecdotally and through papers and that kind of thing. And one is a tipping point in the ocean circulation. And since you're an oceanographer, you're probably aware of the conveyor belt effect, where it sort of evens out the ocean in layman's terms. And having that conveyor belt at some point turn off.
Yes.
That's one. The other one is not so much a tipping point in the temperature of the atmosphere, but in the sea level rise with the Antarctic ice shelf. And the possibility of large pieces of the Antarctic ice shelf coming into the ocean and causing a dramatic rise very quickly. Are you going to get to those, or can you discount some of those?
Yeah, those are great questions there. Let's see, I've got let's see. I thought I had some slides here that would be, oh yeah, here, AMOC here. Yeah, this is a depiction of the ocean's thermohaline circulation, which Chuck was referring to. And this is sort of the ocean's conveyor belt here. And the tipping point he's talking about has to do with something called the AMOC, which is the Atlantic Meridional Overturning Circulation. So the idea here is if you average across the Atlantic basin here, from North Pole to South, Antarctica, average across there and look at it in a vertical slice, look at the circulation in a vertical slice, it looks like this. So this is Greenland here, this is Antarctica here. This is called the AMOC, the Atlantic Meridional Overturning Circulation. The warm part here, you can think of that as being the Gulf Stream. It's water, warm, salty water moving north, where it sinks south of Greenland, and then it flows all the way along, sort of mid-depths here, back to Antarctica, and it makes a loop here. Well, what's been happening, and the tipping point that Chuck is referring to is, in fact, this was even in a movie. There was a climate movie, I saw it on an airplane one time, and I forget the name of it. But, the people are running around saying, oh my God, the AMOC is collapsing, things are going to happen really bad. In the next 3 days, all hell breaks loose. Well, what they're talking about there is the fact that ice melting here from Greenland is fresh water, and that's mixing with this warm, salty water that's coming up from the Gulf Stream. And because fresh water is less dense than salty water, it's making it more difficult for the water to sink here and form and complete this loop. And as a result, that's causing the Gulf Stream to weaken. And in fact, I mentioned it last week, the Gulf Stream has weakened about 15% over the course of the last 70 years or so. In the movie, it happens in like 3 days. The Gulf Stream collapses in 3 days. You got to get it in the timeline there. In real life, it's going to take a couple of hundred years for this collapse to occur. But it is weakening, and as a result, the Gulf Stream carries a lot of heat from the tropical areas to the mid-latitudes. If you reduce that flow of heat in the ocean, then you got to make it up in the atmosphere, and that happens through stormier weather. That will contribute to more severe storms, particularly in the wintertime. So that is a concern, and that's what's going on there. But it's not something that's going to happen overnight. It's kind of a multi-century kind of thing going on there. The other one you mentioned was the ice sheet and rising sea levels. And let's see here. So I think I've got this is a depiction of the West Antarctic ice sheet. Sea level rise, I talked about it a little bit last week. First half of the century, of the 20th century, mostly thermal expansion of the ocean. Second half of the century, thermal expansion is still occurring, but mountain glaciers starting to melt. First half of the 21st century, the ice sheets melting are a big source, and the Antarctic ice sheet, east and west Antarctic ice sheets, are the world's largest store of fresh water. What's happening is, as the ocean is warming down there, it's causing melting, under the ice sheet. This is called the ice shelf. It's a part of the ice sheet that flows out over the water here. And also, as the sea level is rising, that's pushing that warm water farther back in, which is causing, potentially causes the ice to melt faster. So then you mentioned in glacier, there's the famous Doomsday Glacier. It's been in the news a lot. It's called Thwaites Glacier. It's actually it's a part of the Antarctic ice sheet, but it flows. It's flowing towards the ocean, and it's flowing at a rate of about a mile a year, as I understand. And that's the most active, part of the ice sheet down there. It's a chunk of ice the size of Florida, about 1,000 meters thick. So imagine Florida, 1,000 meters thick of ice, and people talk about the ice sheet collapsing. What if that ice sheet collapses? Now, when I think of collapse, I think of a kid's up on a slide, and they go like that, and boom, out into the pool, and it happens really fast. When geologists talk about collapse, they talk about over many years. So, the collapse of this ice sheet would be over many years. But in fact, if that Thwaites Glacier does flow out and accelerate, and maybe in 5 or 10 years, 20 years, whatever, was to flow into the ocean, it would raise sea levels abruptly by about 2 feet, 2 or 3 feet, which is kind of what we were expecting. And that's a big chunk of what we were expecting by the end of the century. What I talked about, yes.
You say abruptly.
Yeah.
So what sort of time frame is that?
5 years. I don't know. I'm going to say 5 or 10 years. I don't know. It's not going to be like that, but in geological time, that's really, really fast. That's a collapse when things happen in maybe 5 or a few decades, something like that. In the long term, as we talked about last week, sea level rise is the real concern, because as the Earth warms, there's this long time lag between warming Earth and rising sea level. And even when we stabilize the temperature of the Earth by the end of this century, hopefully, the sea level is going to continue to rise unless we're able to cool the Earth back down. Other questions?
When you
Yes.
talk about the Gulf Stream weakening,
Yes.
you mean it slows down, or the temperature differential is less? Or
Yeah, so the question is Gulf Stream weakening, does that mean the temperature differential is less or the current is slowing down? The answer is both. The current is weakened by about 15%. I keep using that number. I think it's pretty solid. And that contributes to sea level rise along the eastern seaboard. I mentioned last week, because the Gulf Stream is weakening because of the fact there is that slope of the sea surface perpendicular to the Gulf Stream. As the Gulf Stream weakens, that's going to accelerate the rise in sea level along the eastern seaboard, which is not a good news story. But it also weakens the flow of heat transport in the ocean to to Europe and to the higher latitudes. There is evidence that at the end of the last ice age, end of the last warm period that preceded our last ice age, it's called the Eemian. They talk about the end Eemian period. There's evidence there that the AMOC did collapse, and that led to extremely stormy weather, tremendous increase of severe storms, because of this fact that if you can't transport the heat through the ocean, you've got to transport the heat somehow. You've got to export that heat from the tropics to the mid latitudes. Right, it's done combination of atmospheric flow and ocean flow. But if the ocean flow shuts down, then the atmosphere has to take up the slack, and essentially you get very severe weather. And there's some evidence for extremely severe weather at the end of the Eemian period, which was about, I guess that was about 100,000 years ago, something like that.
where do you find all these charts that you come up with?
It's a labor of love, I go out there and try to build all this material and try to anticipate questions like have come up for here. But they're out there on the internet. You just have to go out and find this material. Okay, I want to thank everyone for coming, and I really appreciate it. Thanks again. Hopefully you'll come again next week. Next week we're going to talk about computer models, what they're all about, climate prediction, and it'll be pretty sciencey, but I think you'll enjoy it. And then the lectures beyond that are going to be going more into the technology, and then finally the final lecture will be on the policy. So thanks again, everyone.